Thank you very much. Thank you. So it's a great pleasure to be here to address you in this interesting and, for me, unusual sort of meeting, and I'm grateful to Donald for inviting me. I think that we may indeed have a lot to discuss in the 1 hour. So we had a great introduction. It's a very nice talk. I love the lymph node data as well, because this is something that's a bit controversial in monkeys and in humans, but one can sometimes clarify things in mice that could be translatable. But they usually make very poor models, so I think that humans would be good models for companion animal aging, and that's the basis of our belief that what we know about humans is more relevant to companion animals than what we know about mice would be. So I'm going to talk about the implications of this immunosenescence phenomenon and inflammaging for immunization of older individuals. These will be humans, so my disclosure is that I know absolutely nothing about dogs, cats, and nutrition, so I'm going to be giving a rather iconoclastic view of human immunosenescence, which often perhaps leads to a different interpretation of the kind of results that Donald just presented to you, which I call sort of the textbook approach. So to start with something that's completely not controversial, it's obviously clear that resistance to infectious disease of many different kinds, or all kinds, probably decreases with age, both severity and frequency in humans of these diseases. These are common diseases from the sort of Bible of geriatric medicine that all geriatricians have at their bedside table, I'm sure. And this was, of course, dramatically illustrated by the COVID pandemic, which offered actually many very rare opportunities to study what happens when the human immune system is confronted by a completely novel pathogen, almost completely novel. Very few individuals are found who did have T cells, memory T cells, that cross-reacted with some components of SARS-CoV-2 because they had been stimulated by coronaviruses, related coronaviruses that give you common colds. And this is the direction probably that Arcturus is now evolving towards. So I'm able to be here today, having had a second bout of COVID recently, probably Arcturus, just like a really heavy cold, and enabling me to talk to you, probably with coughing. That's why I'll stand away from the microphone if I have to cough. So as Donald pointed out, and these are data then from unvaccinated people. So these are people who have not been exposed, almost certainly not been exposed. These are data early on from the CDC in the US, looking at a very large number of people and saying, okay, people at 5 to 7 years, 17 years old are the baseline here as the value of 1 reference group. So very few had serious problems. But if you look at 85 plus years old, hospitalization, and the fatality rate is incredibly 8,700 times higher than the reference group of 5 to 17-year-olds. So what is going on? Clearly, there's a big difference between, especially older men, still a puzzle as to why that is, and being much worse off when confronted with this novel pathogen. So why is that? Okay, there are many reasons, and is it at least partly because of age-associated alterations to immunity, as we were just learning about, called Inflammaging, dubbed Inflammaging by Claudio Franceschi, who's made up lots of interesting names for these kinds of things. Chronic low-level dysregulated inflammatory processes, we can define inflammation as that. And immunosenescence, which we could define as changes to the distribution and function of immune cells, as the textbook view would have it. So when considering all these data, we must always ask ourselves what's not only different, but actually clinically important in older individuals. And that's a much harder question to answer, of course. So a potted view of a T cell response, which is partly also relevant to B cell responses, is that you have to have a very small number of clonal T cells with a particular T cell receptor specificity, simply because there's not enough room. The universe of antigens is so unlimited that you can't have a very large number of cells that would be specific for each of those different antigens that could possibly be, that the system could possibly be exposed to. So when an antigen is detected in the lymph node and stimulate T cells, then you have to have a period of very vigorous clonal proliferation to generate enough cells to be able to counteract the pathogen. If that's successful and the subject is still alive afterwards, the clonal expansion must be countered by clonal contraction to get rid of all these excess cells that you don't need anymore, leaving memory cells that stay in the body for possibly a lifetime, depending on the pathogen, maybe not a lifetime, but an extended period of time. And that would be the case with intermittent re-stimulation. If you're exposed to a particular pathogen in your childhood, when the first contact with the environment is taking place, you're surrounded by, let's say, tribal pathogens that are common in your group of individuals. And thereafter, and this is one reason I think that we have the evolutionary explanation for thymic involution, it's dangerous to generate naive T cells because you might generate autoimmunity. Selection in the thymus for cells that don't recognize self alone is not perfect. So you have to have recognition of combined self plus antigen in the thymus. If that goes wrong, it's a dangerous thing. So you need to have a generation of a full repertoire of memory cells for those pathogens that are present in your tribal area. After that, in the wild, you probably wouldn't be exposed to too many new antigens, new pathogens, so you can turn off this process of generating new T cells. But if you have a chronic infection, then the immune system is constantly re-stimulated and enters this phase of what's called exhaustion and senescence, when this applies to antigens that cannot be eliminated, such as herpes viruses like cytomegalovirus, Epstein-Barr virus, and so on. But intermittent re-stimulation by re-exposure to 10 years later or something to the same pathogen that you saw as a child will not give you a problem with T cells. That's something that was unexpected, was only published a few weeks ago, that new data show that intermittent re-stimulation of T cells does not result in this exhaustion and senescence induction. And in fact, these people who are doing this study, just published in Nature, transferred the same T cell clones through many different mice and found that they were not compromised in their reactivity, but that they could essentially continue indefinitely through many generations. They did this for 10 years, and the T cells were still going. There were hundreds of cell divisions, no Hayflick limit, no stopping of their no clonal deletion, and no exhaustion. So the immune system has a capacity, really, probably to provide lifelong memory and lifelong protection against those pathogens that you had seen in the past. So I can skip this. I think we heard that the bone marrow is altered in aged individuals. There's more production of hematopoietic stem cells rather than less. They're more active. They're more stressed out. The balance of cells that's exported to the periphery changes. More myeloid cells and fewer T cell and B cells, fewer T cell progenitors and fewer B cells with age. So you would think that this would make a big difference, of course, to the way that the immune system is working, and very few recent thymic immigrants, as described by Donald in the previous. So the thymus shrinks. This is a developmental process. This is not aging per se. This is, as I've outlined, in addition to what Donald was saying about the evolutionary reason we believe that this is happening. And however, the result, of course, is that you have fewer naive T cells in the periphery. Therefore, you also have a constricted repertoire, as demonstrated also in the dogs and in other animals and in humans as well. So you have a lot of biomarkers of things that you know are changing with age in most humans and most animals probably as well. As far as the little bit that we know about dogs, cats, and horses indicates that this happens in those animals as well, and mice, of course, and monkeys as well. So I want to spend a bit of time on how we really can measure the distribution of these different sorry, got my little red spot here. So these are original data from our studies of the Berlin population, cross-sectional study comparing young people, 25 to 35, with older people, 65 to 85, at baseline. It's a longitudinal study that will be followed up. And we're looking here at the distribution of CD8 positive, those are the MHC class 1 restricted cytolytic T cells, antiviral T cells, for example, N is naive T cells that have not yet seen their cognate antigen. They're waiting to be stimulated. And these are the intermediate stages, central memory and effector memory cells, that you can detect in flow cytometry by the balance of certain molecules on the cell surface that we don't need to discuss in detail right now. And there's the so-called TEMRA cells are those that are end stage, late stage differentiated. They may well contain exhausted and senescent cells, but they're not all exhausted and senescent. So then Y is of young, of course, here, and old, O is old. We see that in young people, there's a higher frequency in this case of CD8 naive T cells than in old people. Now we have this minus and plus here. Minus means not infected with cytomegalovirus. Plus means infected with cytomegalovirus. So this is in Western or in industrialized countries, people are quite often CMV negative in youth, and the older you get, the more likely you are to become infected with cytomegalovirus. Usually without any symptoms at all. It's a co-evolved virus. Every mammalian species has its own specific CMV, so it's also applying to dogs, cats, and so on. So even in younger individuals, there is a decrease compared to CMV negative people if you're infected with CMV. Other herpes viruses such as EBV and HSV, VZV don't do that. It's only CMV, as far as we know, that does that. Why it does it is a puzzle, but it means that because the frequency of infection goes up in the population with age, if you don't take that into account, you can see the effect of CMV infection rather than the effect of age, so it's a confounding factor. So in older individuals here who are remaining CMV negative, and in the West, in clean, in hygienic environments like Germany, for example, older people may be found who are CMV negative. In India, Pakistan, and so on, you never find anybody who's CMV negative at that age or even at a younger age. So you can see that indeed, yes, the frequency of naive T cells does go down with age, but if you're CMV infected, it goes down even more. If we look at the reciprocal picture of the late stage differentiated cells, young people who are not CMV infected have very few of them because they haven't yet been exposed sufficiently to generate memory cells and lose their naive T cells. So there's very few of these late stage differentiated CD8 cells in younger people who are not CMV infected. The few who are CMV infected do have more. So CMV can drive by itself, independent of aging, this kind of accumulation of what some people call senescent CD8 cells. Older people, the few that you can find who are CMV negative, they don't have very many of these. So it's really CMV that's driving this accumulation of late stage differentiated CD8 cells. So why am I belaboring this point? Just to show you the data. Also to show you, of course, these are hundreds of individuals, about 800 younger and twice that number of older people. So you can see from the error bars there's huge inter-individual variation, always the case in humans. So you have to follow individuals really in longitudinal studies to find out what's really important. Otherwise you get a very broad view and find difficulty in getting statistical significance. So okay, these are biomarkers. These are peripheral blood T cell distribution patterns. So what does that mean? Less naive T cells might mean a lesser chance of responding to new antigens, but we don't know that. It's an assumption unless you can prove it. And similarly, the old people might have a problem with memory cells or lack of naive T cells. So biomarkers are only relevant if they correlate with a robust clinical outcome. And that's a bit difficult to establish in humans, but what we did was to look at older populations for all-cause mortality. So this is unequivocal. You're either dead or alive. It's not a cat, the Heisenberg cat at least. So you can correlate these patterns with all-cause mortality. And in the very old Swedish population, this early study that we did, one of the first longitudinal studies to look at this, we identified a cluster, very simple in those days, simple still immune parameters that correlated with 2, 4, and 6-year mortality in this old population. We call this the immune risk profile, the IRP. This was an inverted CD4-8 ratio, not caused by a loss of CD4 cells as in AIDS, but by accumulation of these late-stage differentiated CD8 cells. And a poor mitogen response, poor clonal expansion when stimulated with mitogen. This was because those late-stage CD8 cells don't proliferate very well. But it's also low B cell numbers and CMV seropositivity, but nothing to do with decreased frequencies and indeed absolute numbers in this case in the peripheral blood of naive T cells. They did not form part of the immune risk profile, at people who are already 85 years of age. So these are selected populations, selected for longevity. Even in Sweden, the average lifespan, life expectancy, is less than 85. And these are mostly women because the men had all died by then. These are people who were born at the end of the 19th century. So the socioeconomic environment was very different then. So actually this correlation of the IRP with survival was not terribly impressive. It was statistically significant even in this small number of people because it's a longitudinal study. So the Octo study was highly selected, people selected for good health, whereas the Nonna study was more representative of those still free living but who were not, many of whom were frail in the kind of average way. So you can see that people who were in the IRP did have worse survival, but it wasn't so impressive that you could say on an individual basis this person is really going to be having a problem. So it was a start. Then we asked the question in a different population, not Swedish, but now Dutch population, the Leiden 85 Plus study, also a fantastic longitudinal study. Very difficult to do these, very expensive to do them, scouring the world for people who are running these studies. So these studies have all been supported by different EU collaboration projects in Europe. So the question is, naive T cells did not seem to be relevant for survival of 85-year-old people in Sweden. How was it in Leiden? And is it that it's maybe limited to a certain population and so on? So these are now people who were also 85 at baseline, and these are the naive T cells, lower or higher frequencies than the median. And as you can see, it doesn't make any difference to your survival whether you have more or less naive T cells. So are there more suppressive cells dampening immune responses in older individuals? Remember that there are more myeloid cells produced by bone marrow in older individuals, in mice and in humans. Myeloid cells, when exposed to an inflammatory environment, for example in inflammaging, we have higher levels of IL-6, CRP, etc., become suppressive, myeloid-derived suppressor cells. So that could be dampening immune responses in older individuals. It's very under-investigated. There are a couple of studies that such MDSCs might be present at higher levels in older individuals, and also that regular CD4 regulatory T cells are present in higher numbers. So we looked at this also in those Leiden 85 plus study. These were people who were 90 at the time of baseline. 0 here is 90 years of age. This is a clustered phenotype that usually represents an active sort of CD4 positive T suppressor cell, T regulatory cell. And here again you can see that it doesn't matter whether you have higher or lower frequencies of these suppressive cells. So it's not that you are unable to make a response as an older person because it's being actively suppressed, at least in this particular study. And I emphasize that all these studies can only be applied to the population and the birth cohort in which you are really studying them, because there's a great deal of variability in, for example, the socioeconomic conditions. If you look at people of 85 who were born in 1890 versus people of 85 who were born in 1920, then things are going to be different, and they are indeed different. But I won't be able to show you that in this presentation. So then we saw, do we know that the commonly observed accumulations of these late-stage CD8 cells that are CD28 negative, often taken as a marker for senescence because this is a co-stimulatory receptor that's required to activate the CD8 cell when stimulated via the T cell receptor. So they're often simply referred to in the literature as senescent, but I would advise caution in accepting this as a definition, because clearly they're often not. So they're not actually, some of them might be, but there is no accepted marker really for senescence in T cells except good old senescence-associated beta-galactosidase, a mysterious version of galactosidase that seems to appear in senescent cells, fibroblasts, and also T cells. So are they actually bad for you? Well, yes, by association they are, because of the Swedish immune risk profile was characterized by an accumulation of this type of cell that tipped the CD4/8 ratio and correlated with all-cause mortality in older people. And they may be also, in some more recent data that we've generated together with our Canadian colleagues, might actually have a mechanism for why they are bad for you in the case of influenza infection. So in this particular instance, late differentiated CD8 positive cells that are specific or are specific for viral antigens like COVID, like SARS-CoV-2 rather, and influenza, they are required to clear infected cells that have avoided antibody protection, for example, after vaccination. So they are characterized by being CD28 negative, by expressing these two surface markers here. Doesn't matter what they are, but they are present on these late-stage differentiated cells. These are the ones that might contain senescent cells. So they always retain the same T cell receptor levels, the same T cell receptor activity, the same T cell receptor specificity. Unlike B cells, T cells do not change their T cell receptor specificity as they undergo clonal expansion and contraction. They stay the same. So they still recognize the same antigen, but other things are changing in these cells. And we see that the activated cells that are present in younger individuals carry perforin and granzyme B. This is the mechanism by which these cells kill their target cells. So the T cell receptor recognizes the antigen on the surface of the target cell, brings in the perforin molecules that punch a hole through the membrane of the target cell, and the granzyme is squirted in, which kills the target cell. So in older people, however, one sees the same T cell receptor, the same specificity, the same recognition. They're also full of granzyme B, but they don't have perforin. So they recognize the target, the mechanism for triggering cytolytic activities is initiated, the granzyme is shot out, but it is not going into the target cell, it's going to the interstitium. And this causes a granulopathy that creates inflammation and tissue damage. And we believe, there's no proof yet, that this is one reason why older individuals have a problem with dealing with influenza infection in the lungs. So is there a survival advantage or disadvantage in older populations for the presence of this type of CD8 positive effector memory cell? Again, this is the Leiden 85+ study, high and low, and now you can see there is a clear difference. If you have more of these cells, then you are likely to survive longer than if you have fewer of them, suggesting that what's important in older people is retaining memory for antigens that they'd seen in the past, maybe re-exposed to, like flu, control of CMV and other antigens, other pathogens. And that's what's important for older people. If they're exposed to something like SARS-CoV-2, of course, then they don't have defense because they may actually not have T cells remaining in their repertoire of naive cells that are required to see a new antigen or new pathogen. And that's one reason why perhaps older people are much more susceptible if they're not vaccinated. So inflammaging is usually considered to be bad. Higher levels of inflammatory mediators are bad. But inflammation is, of course, a natural and necessary result required for an effective immune response. So we asked also in this older population, Leiden 85+ study, is there a significant advantage in survival for people who have the ability to respond against a common CMV antigen, this PP65. Everybody who's CMV positive has T cells responding against this target to control the CMV positive cells so that CMV does not reactivate. And everybody in this study, it's an in vitro stimulation study exposing cells from these individuals to this particular and specific stimulatory antigen, and then looking whether they have a pro-inflammatory response measured by release of TNF and IL-2, for example, or whether they have also an anti-inflammatory response. So you always have to look not only at the pro-inflammatory response like IL-6 and TNF, but also the anti-inflammatory response like IL-4, for example, which dampens that. So you can see here, very few people, but it's quite clear that for individuals who have both, they have the same inflammatory response, but they also have this anti-inflammatory component, and their survival is much worse than those who have an unopposed pro-inflammatory response. So here, inflammaging, so to say, is good for you under these circumstances. So how does this all relate to vaccine-induced immunity, which I was really meant to be talking about? Of course, you introduce your pathogen in a controlled manner. It has to be picked up by dendritic cells, go to the lymph node, I won't belabor this point. Donald mentioned all this, and the fact that the lymph node, the antigen-presenting cells may be a problem. Actually, the mobility of the dendritic cells to the lymph node carrying the antigen might be a problem as well. Some evidence for that. Problems in the lymph node, stimulatory signal problems, all manner of loci where there could be a difficulty in generating an adaptive immune response. So if fewer naive T cells in the blood of older individuals are not part of the IRP, are they really a problem for responses to neoantigens? So they might be part of the problem, but we know that vaccination against neoantigens can be highly effective. Thank goodness, 1 year due to the fact that RNA vaccines have been developed for cancer vaccination, plug in the spike protein that BioNTech did and that CureVac was doing in Tübingen, and also Moderna, and in a very short time you have an effective vaccine against SARS-CoV-2. So effective that, for example, in this early real-life study from Britain, over 170,000 individuals, very old, 80 to 83, getting up to that 8,700 times worse survival compared to the control the reference population. You see here that the unvaccinated control versus the vaccinated control, vaccinated population is very different. The vaccine is very effective also in older individuals in terms of hospitalization and mortality. There is an age effect, though. This is a measurement of the antibody response to the BioNTech vaccine or to the AstraZeneca chimpanzee adenovirus vaccine, not an RNA vaccine, but another different sort of vaccine. And the response, the antibody titer and the duration of the antibody response, even the difference between young and not even middle age is already noticeable. So it is the case that older individuals, even if they can respond and there is an effective protection, they still have a lower level of antibody production and a shorter duration of response. And this is also reflected at the T cell level, that it's not as strong in older individuals. So there is an age-associated difference, but it doesn't really matter. You've still got enough there to protect. So older individuals vaccinated twice with the BioNTech vaccine are almost as well protected as younger individuals, despite the fact that there is some lesser response to be measured, but it doesn't matter clinically. So if the naive T cell repertoire is not the whole problem, it sometimes could be a problem. Is there a problem with immune memory in older adults? So the duration of protection after vaccination or after natural infection is different in different pathogens. We don't know why that is. We certainly know that measles will last a lifetime after natural infection. For many of these common diseases, we don't know how long the vaccination protection will last because the vaccines haven't been around for long enough. But it's clear that there's variability, and we don't know why that is, why different pathogens, there are many speculations as to why that is. To get back to this picture, you're getting exhaustion if you have chronic stimulation. So if there's re-exposure too frequently or it's a chronic infection, then this could dampen down the immune response by creating exhausted T cells that don't work properly. But again, the intermittent stimulation, I'm referring again to this Nature paper, shows that that doesn't necessarily happen if there's sufficient time between antigen exposures. T cells recover and they will continue forever, apparently. But we also know that if you have chickenpox as a child, you're likely to have a VZV reactivation at some point in later life if you're stressed out or something like that. And this can be extremely, shingles can be extremely painful and damaging, reducing life, not life expectancy, but quality of life. And this we do know is a failure of CD4 positive interferon gamma producing T cells. So it is a failure of immune memory that doesn't keep this virus under control. But recently, also a better vaccine was introduced, not using RNA technology, but using recombinant antigens. And this was licensed in the 2015 or so. The test here, this is the licensing program study. 70 years of age, people 70 years of age, placebo versus the new vaccine, they are fully protected. So older people who were not revaccinated do show a memory deficit. It's not because the memory T cells aren't there. There's some other reason for this lack of effect, which can be rejuvenated, so to say, reactivated by an appropriate vaccine. So we come to the conclusion that in certain circumstances, responses that are missing and are clinically relevant are missing for a reason other than the fact that they're gone, but they can be reactivated if you get the right stimulus, if you get the right vaccine. So we need better vaccines. Influenza is usually a problem of older adults, as was mentioned earlier. Hospitalizations and deaths are not much of a problem in younger people. Vaccines are seasonal vaccines. The classical old-fashioned form of seasonal vaccine against influenza is very ineffective in the elderly, but it's also very ineffective in younger people. So there are many reasons for that, and clearly one needs to have better influenza vaccines, and many people, many companies and many individuals are working on that to translate the RNA technique to using those same products for influenza and for reducing the reliability of the vaccine on the identification of a seasonal strain that might become or might not become prevalent in the future. So we need to have a universal influenza vaccine, so there's much activity there. What we know at the moment, though, is that these vaccines are really bad, but are they really less effective in older than younger adults? Is it age or is it something else? And to cut a long story short, without going through these slides in too great detail, it's not necessarily age per se, but it's geriatric frailty that correlates with the inability to respond as well as you could to such an influenza vaccine. So a lot of studies, very difficult with influenza due to annual revaccinations with different strains, and depending on the strains in circulation that year, very hard to analyze. But with the input of the Canadian group that used to be led by Janet McElhaney, a lot of information has emerged which suggests that it's a question of the health status, not necessarily only the immune health status of the individual, but health status that can be captured by these scales of geriatric frailty, which impact on the ability of an older person to respond. So of course, the older you are, the more frail you are, and that is what is correlating with your inability to respond very well to the influenza vaccine. That was shown on that slide there. So if you adjust for the level of frailty in your test population or in your study population, then vaccine effectiveness in older and younger adults is not so different. So it's not age per se, it seems to be whatever frailty might be doing. But things are, and by now you won't be surprised to hear that they're not as simple a picture as you might wish to have. So in this kind of heroic studies that are done with over many years, only with NIH support for programs that run for, I don't know, it's been running for at least 3 5-year seasons. This is comparing standard dose vaccine with high dose influenza vaccine that's tailored specific or is licensed specifically for use in older individuals. It's just doubling the dose of the antigen, that's all. Making a better vaccine by increasing the amount of antigen in it. And in this study, one can see, without showing all the actual data here, that in older people, the response to the standard dose vaccine is no different according to frailty or according to any of those parameters that we're looking at. But to the high dose vaccine, it is, and you do see differences in the high dose vaccine group, but not the standard dose. So this is an illustration of how sensitive these assays need to be, taking into account something you would think was not really terribly important, whether you double the amount of antigen or not in your vaccine, but it makes a big difference to the outcome. So here you can see a summary of one of these studies. According to a particular frailty index, and there are several competing frailty indices, as geriatricians are aware. So this is a particular one that was used for this study. Just draw your attention here to pre-frail versus robust and frail versus robust. And you can see here that this is now a readout that's not to do with antibody titer, that's a surrogate for protection and might not actually always work in the elderly, but actually laboratory confirmed influenza illness. not just people saying they've got the flu, because they often don't have, but you have to confirm this in the lab, so it makes these studies also more difficult. And you can clearly see here that there is an association between responsiveness as judged in this manner, protection actually against disease, and frailty. No surprise really that a frail person is likely to be worse off when sick or when getting sick than a younger person, but it's hard to show that that's really the case, and you need to have these data to be able to make a proper case. So now we have the question of what is chronological age, what is biological age, what is the relation of those two parameters to frailty. This was discussed yesterday in the context of biological age versus chronological age in some detail. So if we do that in these flu studies, I won't go through those details, that was discussed yesterday. It's simply taking a set of parameters, in this case shown here, these laboratory values here, and normalizing them to what would be the average group values for people of a certain age, and then taking your individual, do they have a pattern that looks younger or older than that age? So you can separate biological age from chronological age in that way, and correlate that with frailty. I won't go through the details here. If we do that, this is the Berlin aging study again. I showed you some data right at the beginning on the distribution of T-cell subsets in the Berlin aging study. It's a really nice study that's still ongoing. And trying to, this is again not to do with flu vaccination, this is all-cause mortality, just to show that the ability to distinguish between biological age and chronological age can be informative in terms of survival here over this period of time. Relative to chronological age, biologically older individuals had on average 1.5 year lesser survival. And when we do this kind of biological age versus chronological age analysis in those individuals with the standard dose of vaccine, a flu vaccine, and the higher dose that I referred to previously, you can see that on average the responses of younger biologically aged, older biologically aged, for the standard dose are not different. We had predicted, of course, that an older biological age would generate a worse response. In fact, we saw the opposite to our surprise, but only in the high dose. So when you get a high dose that's more effective, you see that people who are biologically older responding better. How the hell can that be the case? They're all immunosenescent because they're worse off than the younger people, or those who have a younger biological age are biologically younger. And in fact, this turned out, I think, in these still unpublished data here, that, or they are published, in fact, in the meantime, that this is perhaps a case, again, where inflammation is in fact, inflammaging is in fact good for you. It's enhancing your response. It's a typical immune system effect where you have to pay the price. It's a double-edged sword. You have immunopathology that is the price you have to pay for protection against pathogens. So in this case, the TNF and IL-6 levels, the sort of classical inflammaging, inflammatory type mediators, are higher in those individuals who are responding well to the influenza vaccine and who are biologically older. So perhaps the mechanism is that the biologically older people have more inflammaging, more IL-6, more TNF. That's bad for many things, but it's good for their response to influenza vaccination. So it's good and bad at the same time. So my conclusions are that there are, yes, of course, there are key differences between immune measures in younger and older individuals' peripheral blood, and you can do that. You can see these changes happening. They're not only differences, they are changes that you can see happening in longitudinal studies. Naive T cells go down, memory goes up. Many of these are adaptive changes. The immune system is meant to do that because it learns from, uses up its naive cells, makes memory cells, and is ready for the next exposure. So there are clearly fewer naive T cells and B cells, more memory cells, but there are fewer lymphocytes as well. The distribution of cells coming out of the bone marrow is different. And this is what is often considered to be characteristic of immunosenescence. And there are indeed usually higher background levels of inflammatory mediators, which in epidemiological studies do correlate with more disease, frailty, and worse survival. Nonetheless, immune responses to both neoantigens that requires naive T cells with a repertoire that will see the antigen. SARS-CoV-2 was, of course, the prime example of that. The only way that we could learn that in humans, actually, because otherwise there are very few data that you can gather for individuals who have not been exposed to any of those pathogens. Only yellow fever vaccine was a possibility. So memory responses can be highly effective in older individuals, only if you've stimulated and pre-primed the immune response with an appropriate vaccine. So the message is that we need better vaccines, and those are in the pipeline due to the RNA studies that were pioneered by companies making cancer vaccines. So poorer immune responses of older individuals are not necessarily a problem of immunity per se. They're a problem of the old environment. They're a problem of being able to get the stimulus correct so that you have a vaccine effect before the pathogen arrives and overwhelms the immune system by killing the host before it has a chance to generate a proper immune response. So of the major hypothesized problems with immunosenescence, how important are they really for responses to vaccination? Too few naive T cells and B cells and their poor functionality are not insuperable problems. Compromised lymph node architecture might actually be a big problem, but you still get responses in older individuals despite that. Old blood environment, we didn't talk about, inflammaging, possibly facilitatory, in fact, if you have higher levels of inflammatory mediators. So holes in the repertoire, as it would be called, and poor functionality would not necessarily prevent a response to novel antigen challenge. Too many exhausted memory cells, also apparently not an insuperable problem. Too many suppressive cells, also not an insuperable problem. So the conclusion of this is that immunosenescence is not necessarily something that is not, that you need to do radical rejuvenation technology that many people seem to think is necessary. It's a question of preparing an old immune system in a way that enables it to be reactivated, and for that you would need properly adjuvanted vaccines of a type that you know are going to work. And those immune markers that are used to distinguish immunosenescence, let's say, you could use as biomarkers to follow these kinds of studies in order to generate more efficient vaccines, because clearly you can't only look at the clinical response. You need surrogates so that you know your vaccine is going to work before you have huge deaths from COVID. We'd like to have a COVID vaccine before the next COVID comes, right? So many collaborators, of course, of which this is a small number. This is our little institute in Tübingen. We used to call ourselves the Tübingen Aging and Tumor Immunology Group because we were tatty. In English, that means clothes with holes in. And many of the lab members, some of whom are continuing the good work. David is working for Biorad. Killian is continuing with some of these studies, and other people who were wonderful students and postdocs. Evelina moved to BioNTech, where she was working on the cancer vaccine part, and then they dropped everything, of course, and changed to SARS-CoV-2, but they're still publishing on the cancer vaccine side. So that's where, don't forget that that's where these vaccines came from. It was all to do with cancer research. So thank you very much.
Thank you.